טוב, אני מבין שאנשים מנסים להתחיל קצת בגשם, אבל בכל זאת נתחיל. אז, good morning. So we want to continue the discussion of what we call parameter estimation. And I assume Noga actually showed you a lot of examples and many details that I missed, but so I may repeat some of the things she said, but if you think it's known already, just let me know. So talking about the following essentially Bayesian decision problem, which is somewhat more general. So we have a space of parameters, which is usually some subset of Rn or Rd, and is, as you recall, is spared for the sample size in our course. So we call it Rd in general, where D is the dimension of this space of parameters. So in general, it's some d-dimensional space. And we, in the Bayesian framework, assume that there is some prior over these parameters. This prior is a big headache in this case, because usually it's not really justifiable from what we call first principles unless you have something very, very special and you know your conditions very well. So statisticians usually try to assume the less possible on priors, or choose them such that everything is convenient, as you know. But of course, in some cases, you prefer to talk about estimators which are not Bayesian and don't depend on prior. But we actually assume that there is a prior at this point, and there is a map, a stochastic map, right, or something which we later on call a channel, but it's a map from the priors from the parameters to observations or samples in the context of statistics, it's usually called, which essentially is going through some sort of parametric family. So the parameters are parameters of some family of distributions, like the Gaussians, the Bernoulli, Poissonian, whatever, all the distributions that you have seen before. So this is some sort of parameters and the family of distribution usually specified together. But we generate from this by sampling IID or not IID. At this point, we prefer to usually think about IID samples. We generate some n-dimensional sample space. Actually, both, as I said already, both x and theta can be vectors, can be high dimensional, usually in different dimensions. So think about it as fixed vectors, and this is actually a vector of n independent or not independent samples drawn from this distribution. So we actually, as we said already, I mean, x is distributed with this parametric distribution. That's what we mean by that. Okay? And we saw that what we want is an estimator. And as before, I'll keep here some bracket empty for something else which we already called the statistic or the sufficient statistic, which I'll come later to it much later. But so there may be some functions of the sample, like the sample mean or the sample variance or some other function of the sample, from which we actually estimate. So we generate a function which should estimate our parameters, so we call the estimator. So here I'll call it just in general statistics. And we already noticed such statistic in the case of decision. decision making, which was the likelihood ratio, or the log likelihood ratio. But this is going to be some sort of functions that we calculate from the samples, from which we can generate estimators. And the estimators of the parameters should be, in a sense, our best guess, or whatever we can say in the best possible way, with some sort of guarantees on the value of the parameters from the sample. So the problem in general is some sort of a noisy detection problem, as we'll call it later on. We are trying to estimate the state of the world from noisy observations. Okay? This is a very generic and very general problem. You can think about it in many different contexts: statistics, learning, psychology, perception. This is the basic problem that we do all the time with our senses, trying to estimate the state of the world and act accordingly. So this is really a fundamental problem that we want to be able to say as much as we can about. All right? So we talked about in the Bayesian setting. Bayesian setting means that we have some other things. In particular, we have a cost function. So here we already essentially everything was focused on the statistical model, the prior and the channel, or the parametric family of distributions. But so we have a cost function, which in this case depends on the estimator and on the state of the world, on the parameter. And I omit the vector sign here, but in general think about it as possibly a vector. Okay. And then if we have a cost function, we have the general Bayesian solution, the best possible estimator, provably, is the one that minimizes the conditional risk. So the base, in that case, the Bayes optimal will be something that minimizes all possible values of the parameter, the conditional risk of the estimated. I want to denote it somewhat differently, and that's the conditional given the sum, where the conditional risk was the expected cost with the posterior distribution. Okay, so this is just the argmin of the expectation with respect to posterior distribution of the parameters given the sample of lambda. Okay, so this is good because once we know that this is the general solution, we can simply see what it is in several interesting cost functions. So the first one we talked about last time was what we call the L2. Actually called it MSE, but we'll keep using MSE for something else later today. So let's call it L2 or L2 square. So this cost function is essentially the norm of the parameters of the estimator minus the true parameter square. So we punish wrong estimator by the square of the norm, the L2 norm. Which is, in the one-dimensional case, is simply the theta hat minus theta square, okay, in 1D. Okay. So this, in this case, will be the expected square, posterior expected square. Loss. The risk will be simply the posterior over theta of the square loss. And we actually saw, I think that Nog actually repeated it, no? So I don't have to show it again, that this gives us what we call the L square optimal estimator. V what? What was it? The conditional expectation with respect to the posterior. Okay, so this is sometimes simply called the conditional expectation over theta, p theta given x. So we assume the sample is given. Again, my notation is this notation for the sample. Sometimes we omit the bracket. Don't confuse it with x to the n at this point. This is usually not the case. Okay, so the conditional expectation over this posterior is important. The posterior, which means it includes the prior, through Bayes' rule, of what? Of theta. Okay, so this is the conditional mean or the conditional expectation. It's a very important property. Okay, so this was the L square, and you can ask all sorts of questions. What's so special about the L square norm? The L square norm is the most important thing about it. It's simple. I mean, you take the derivative of square, you get linear equation. So this is why we really love it in all sorts of applications. It's sensible. I mean, okay, square error is something which makes sense in many cases. For example, in many physical cases, the square error is somehow related to the amplitude square of something which is related to energy. For example, the energy of. So in many cases, minimum energy and minimum square are very similar. If we are talking about energy, which goes like the square of the amplitude, which means things like harmonic oscillators, or in the linear physical theory, essentially, that's what it is. But of course, besides the fact that it's easy, it's also going to be related, and it's related very closely to Gaussian distributions. So, and Gaussian distributions are important. They occur in nature many, many times, not always, but due to the central limit theorem. So whenever we have sums of independent variables with very weak assumptions about them, they tend to just distribute Gaussian, and then other things will have the same property as L square. So L square is not just convenience. It's not a coincidence that both of them, I mean, the L square estimation and the Gaussian distribution were invented by Gauss, and this is really one of the most fundamental, most practical measure of cost, especially in engineering, but everywhere. And so it has many deep links to linear systems, to linear physics, I mean, harmonic oscillators, to energy, to many other. So usually there are good reasons for doing it, but whenever you do it, you have to know why you're doing it, other than convenience. And then we mentioned lambda 1 or L1, which I didn't show much about, but we had an exercise which was essentially the L1 norm, which is somewhat penalizing deviations in the estimator less strongly than the L square norm. It's going slower. It's going like the distance, not the distance square. And in that sense, it's more sensitive to large distances, and less sensitive to large distances in that sense. So in some cases, we call it more robust. And actually, there's a whole branch of statistics called robust statistics, which is based on things like this. I mean, you don't want to be very sensitive to outliers. The L square is going to penalize you very, very strongly, like the square of the distance, if you're very far away from what you want. So the L1 is going to be more tolerant. And as we saw, or you will see in the exercise, the estimator here is what? It's what we call the chetzion, how do we call it? The median. So the median theta, easily defined in one dimension. In more than one dimension, you have to think a little bit. What do I mean by this? So in one dimension, it's precisely the point that splits the distribution into equal masses. Okay, 50% is above and 50% is below. Which, by the way, can be, in some cases, very bad, because just like the mean. I mean, if the distribution has, let's say, two bumps made up of two Gaussians, this estimator, both the least square and the L1, will give us something which is very unlikely, just in between them or something. But in normal distributions, I mean, in the sense that normal, not only Gaussian, but have a big bump around the mean, then both of these estimators are normal, and the median is somewhat more robust. That's why when we have some suspicion that our distribution is not Gaussian, like in economy or in finance, usually the median is a more robust statement. If you talk about not the mean income, for example, but the median income, tell us a lot more. Okay. So the median, this is something which is not hard to show in one dimension. In more than one dimension, you have to think what you actually mean by median. But I'll leave it for you to think about it. And then we had something which I started to talk about, which we call the maximum a posteriori, or when we talked about lambda, we generalized somehow the notion of error, probability of error in the Bayesian diffusion case, which means you just want to penalize very harshly whenever theta is not theta for errors. So, I wrote it as 1 minus the Dirac delta function. I think in one dimension for a second, here the generalization to higher dimension is easy. And this gives us an estimator, so theta estimator, which I'm going to call the maximum posteriori, or map in general, is in this case, what is it? So I don't know if you saw it in the exercise or not, but it's easy. So the conditional risk in this case is simply the integral. And as I said already, I mean, this has a meaning only inside integrals. So if it's not an integral, think about it as the Kronecker data, if it's a sum over discrete spaces here. But since we usually assume that theta is continuous, even for discrete distributions, even for when the variable x is discrete, we think about theta as continuous parameter, like conflicts or whatever. So so this is going to be simply 1 minus delta theta hat minus theta, the symmetric function usually. So then the posterior, and we integrate over theta. And what is this? So this is simply 1 minus. So the first one is simply 1. So the integral of theta over theta is 1. Okay. And the second one is what? So what the delta is doing? It simply replaces the estimator by the value in which theta is the argument of the delta is 0. So it's simply p of theta hat. Okay. Sometimes, especially in Amir's notes, we make a slightly more careful distinction between density and probability. Probability function are usually spelled for discrete spaces, and density is continuous spaces. It's true that we have to make the distinction, but like a good physicist, I'll assume that you understand it from the context. If it's a density and integral, or discrete distribution and sums. Essentially, it's all the same. We have to be careful when we start talking about entropies and things like this, but at this point, it's all right. So what's going to be? It's going to be the argmax of this. Argmax over theta. Argmean of this, or argmax argmean of this over theta hat in this case. Yeah, theta hat is a bit notation here, but never mind. No. This is the argmean. Yeah, it's all right. So this is theta hat map. Okay, it's a special theta hat, And of course, the argmin of this is the argmax over theta hat of this. I can eliminate the hat here. The argmax over theta of this. Okay? So it's the value of theta for which P is maximized. So it can be very different from the mean. For the Gaussian case, for example, it's usually the same. The mean and the maximum are at the same place. But in this case of two bumps, it may have two different values, the equivalent, or it's actually the maximum of the distribution. Okay, maximum of the density. Sorry? So this is the theta map. Of course, what we usually say, you talked about it at Nova, I guess so. So I don't have to show you an example, or do I? Okay, the example takes more time, so I leave it to Nova, but or to yourself. But so you saw an example this of, let's say, the exponential family, exponential form, exponential distribution, or the Gaussian distribution, or something like this. If not, you should. I'll show you one in a minute. But what is good to note is that, of course, this argmax is equals to the argmax of the posterior of the prior times the likelihood. Okay? So I can ignore the normalization. Why can I ignore the normalization? This doesn't depend on theta. Okay, so, and of course, it's easier to see if you take the log. So it's the argmax over theta of log P0. Why it's the same argmax? Sorry that I write in this corner, so you have to, those who sit there should believe me. So again, and the argmax is argmax of the log over theta, of the log of P0 of theta, plus, I'll write it again, the log of the likelihood. You already know that this function is simply the likelihood of the data. Okay? But at least in the case of the IID samples, so the argmax over this is simply the argmax of the log prior plus sum of the log excited. So this is here, it's IID, yeah. So far I didn't assume it, here I assume it, okay? So in general, this behaves like what? As a function of n at least. So this is a sum of IID numbers, and as such, it will grow like n times the expectation. Okay, so this will be the argmax, or this will behave like the argmax of log P0 plus n times the. Let me denote it by this. I know this is a notation that is you may not be familiar with, but you may not like, but if you're a mathematician, but it's very convenient. over x. So when I say there, when I say something like this, I mean this is asymptotically true for large n. Yes.
Why is there equality between the last two lines and the one large? The last two lines and the one
Here?
Yes.
Why is this? So first of all, it's argmax of both of them, yeah? And this one. So this is a sum of IID numbers. Here.
Yes, the label one.
So I said, okay, I'm using Bayes formula, and then I ignore the denominator. So I'm talking maximum. So the denominator is just a function of the sample, it's not a function of the parameter. It's important. So I don't need to worry about it. So this is Bayes plus the fact that if I take the maximum, Pxn doesn't depend on theta. So it's not going to affect my estimate. Just to save some writing. We do it all the time after you get used to it. So what is important here is that this grows usually linearly with n. This particular function we'll see again and again. It's the expectation of the log probability. It's something some of you already know is related to the entropy. But if you don't know, forget it. I know that you're taking, some of you, many of you take Yoram's course in parallel to me. So it's actually preparing the ground for a lot of information theoretic. This is an important function on its own. But what is important now, this is some sort of a number, this expectation, and it's O1. And it's multiplied by n. So this is going to be O of n, and this is going to be O of 1 if the prior is well behaved. For example, there are no places in this theta space where the prior is 0. If the prior is 0, then I'm not allowed to take logs. I get minus infinity, and this is so good priors should never have 0 anywhere. This is one. If they really exclude part of my parameter space, then exclude the parameter space, and then restrict it to the cases where the prior is actually positive. So in some sense, for large n, for n large, I don't mean really the limit, large enough, this will behave very much like the argmax over theta of this, because this is negligible compared to n. This is xn here. Yeah, okay, xn. So this is asymptotically the maximum a posteriori estimator is going to behave just like this particular thing. It's going to be independent of the prior. If the prior is assumed to be well behaved, I mean, it doesn't vanish anywhere. So so this calls, especially if you are not Bayesian, it calls for a much simpler estimate, which is not a Bayesian estimate, but it's very, very important, which we call the maximum likelihood. So the maximum likelihood estimate is the thing that maximizes this. Well, this is, again, asymptotically the same. So the correction of the prior, and you saw one example of this at least, is usually like adding dummy samples to the sample or something like this. It's adding some information due to the prior. If the prior is, for example, in the Gaussian case, if the prior is just a normal 0-1 Gaussian, then it's going to add 1 to the sample. If it's a different prior, it's going to add something else. But so the prior is giving a small tilt or a small shift to the estimator of the maximum likelihood, which in generally, due to this property, in the IID sample case at least, it's going to vanish this shift asymptotically. So it's called, sorry? So far, I didn't put, you're right, that in some sense I would like the log likelihood to do it per sample. So I'll divide it by n, it's convenient, and we'll talk about it in a second, because the log likelihood is going to increase like, at least in the IID case, it's going to increase linearly with n. And so talking about asymptotic thing is a bit off. It's going to talk about infinity, so it makes perfect sense to divide the log likelihood by n. And we'll do it in a second. If n is fixed, it's not going to change the estimate. Okay. But so far, I was talking only about. So the maximum likelihood estimate. This is the definition. Is the thing that maximizes the likelihood. Which is the same as maximizing the log likelihood. because log is a monotonically increased function. And if you are not sure about it, convince yourself that any strictly monotonic function will not change the position of the maximum. It's nothing more than the chain rule of differentiation, if you want. So this is the same as this. And as I said, for IID, this is going to grow with n, linearly, asymptotically. And grow or decrease is actually usually decreasing with n because it's a negative number. And the log is a negative number. So so in many cases, it makes more sense to talk about the log likelihood function per sample divided by n. So where n is fixed, this is the same as the argmax over theta of 1 over n log pxn. Of course, if n is fixed, it doesn't change anything.
Could you repeat your last statement, please?
From here to here?
Yeah.
N is just a positive number, fixed number, so multiplying by it will not change the position of the maximum.
That's why
But since this in the independent case, as we saw here, this is growing linearly with n. So this is a function that is going to be for a large number. It's going to grow with n. So we want a function which we compare for different sample size, for example. So if you divide it by n, we don't change anything. It's just as far as the definition here. So this is an O1 number in the IID case, and it doesn't grow with n. Okay? Of course, the variance is something different. All right, any questions about it? So this is, as I said, this is the maximum likelihood estimator. And without exaggerating, it's really the most important practical estimator in all practical application. This is what people do without thinking all the time. This is the first thing you want to do. Now, as I said, maximum likelihood estimator is not strictly speaking a Bayesian estimator because I ignore the prior. But so it's a close relative of the map, the maximum a posteriori. And in cases where you actually care about the prior, you should really take the map, not the maximum likelihood. But in most cases, you don't want to know, you don't want to assume anything about the prior. So I actually wrote here a lot of examples of maximum likelihood estimators. I simply wonder how many of them I really have to do it. So, for example, the maximum likelihood estimate of a Gaussian. One example I do have to show. So, example.
This one you don't have any cost function.
No. So it's not a Bayesian estimate. It's an approximation, in some sense, an asymptotic approximation of the map, maximum posteriori, which is Bayesian. In some sort, it's an extension or some sort of a limit of the map estimation. But since it doesn't assume anything about priors, it's very convenient. And it's much easier to calculate in many cases. So let me see if I can give you a simple example. So yeah, I'm running late, but a simple example is for example, is let's say the mean and the simple and very important examples are the mean and the variance of a normal distribution. So let's assume that px theta is actually this two-parameter family theta 1, theta 2, where this is normal with mean mu and variance sigma squared. So how much of it you showed or you showed or gave them to do at home, I don't know. Yeah, so this is theta had and this is theta Schneider. I'm not going to confuse you here. I can, but I don't want to. Okay, so theta, this is the natural parameters of the Gaussian distribution. Okay, so what are the maximum likelihood estimates in this case? How do I derive them? So I write the likelihood function. So the likelihood given this theta 1, theta 2 is what? So it's the product of the I assume IID, of course. I don't always need to assume IID, but here it is. So it's a product of Gaussian. So the product 1 of this 2 pi sigma e to the minus x minus mu square over 2 sigma square. I hope that there's nobody here who doesn't know it by heart. And xi, of course. And this is because it's of this. No, it's IID. Only the sample change with I. Okay. Otherwise, it's a much harder problem. Each sample is coming from different distribution, then you're in trouble. But at least not for now. So, but this, of course, because of this special exponential form, as we'll call it later on, I can take the product into a sum in the exponent. Okay, so this is 1 over 2 pi sigma to the n. You can put the sigma square inside the square root if you want, doesn't matter. And e to the minus sum of 1 over 2 sigma square, or 2 theta, sorry, I had to write theta 1, theta 2. But okay, you know what I mean. So this is theta 1, this is theta 2, but it's all right. It's the same thing. So this is sigma square, xi minus mu square. Okay, so of course it makes perfect sense in this case to take the log. Okay? It's going to simplify things significantly before I take the derivative. So the log likelihood mu sigma is the log or minus n times the log of square of 2 pi sigma minus some 1 over 2 sigma square xi minus mu square. Okay, so this is the log likelihood, which is usually what you do. And of course, I can divide it by n and put 1 over n here. Doesn't make any change. Okay. So so this is the log likelihood per sample. Okay. And in order to estimate, to get the maximum likelihood estimate, what should I do? XOR. Like my chemistry teacher in school used to say, "Al hachaim ve'al hamavet nigzor." This is a sentence I never forget. It was in my somewhere in high school. It's stuck in my mind. So we take the derivative the first one with respect to mu. Okay. Ignore the 1 over n and so on. So this is independent from mu. This is taking what is going to give us. So it's going to be 1 over minus 1 over 2 sigma square. I already want to make it simpler. So 1 over n sum xi. Believe me that this is what we get. And
the minus should disappear.
That's right. Minus even disappears, but it doesn't matter. You're right. And this should be 0. Okay, because I want to estimate. So if there is a unique solution to this, there's one maximum, or it can be minimum. So if you really want to be careful about it, you have to check the second derivative. But in this case, I know it's a maximum. Personal knowledge. You really can check the second derivative if you want, but we'll do it some other time, or you do it at home. And so it's a maximum. And well, at least this is the only place where so we get the maximum likelihood estimate is the thing that makes this 0, which is 1 over n some xi. Okay? So notice, I mean, you actually did an exercise with the maximum a posteriori or the maximum, the conditional mean. Both of them depend on the prior. If the prior was, let's say, for the mean was normal 0, 1 or something like this, it actually changed this estimate a little bit. It added 1, or it added something here. So this is the maximum likelihood estimate. Is precisely what we call the empirical mean or the sample mean, which is simply the average of the samples. Okay. So this is the sample mean, or sometimes called empirical mean. Okay, so is this clear? It's very simple. It's a little more complicated. I want to do it before the break to estimate the variance, but it's not. It's just the same principle exactly. So how do I estimate the variance? I take the derivative with respect to sigma. Okay, so you have to do it a little more carefully. So in order to estimate sigma, you take the log likelihood sigma and take the derivative with respect to sigma. Again, there's all the necessary assumptions. Sigma is a positive number. Sigma squared. Sigma squared is much easier, which was my theta 2. Okay, so we take the respect to sigma squared, and so sigma squared is a positive number, but it doesn't change anything here. If you want, really, sigma squared should be here. And so what do I get here? So here I have to, maybe I put it back as sigma squared inside the square root and take the square root out of the log, which is half. And then essentially I get half log sigma squared, which is just log sigma. And take the derivative of this. It's just what? So it's 1 over sigma squared. Half 2 sigma squared. This is this derivative. And here you maybe have to be a little more careful. So you really want me to do it? So take the derivative of 1 over x. It's minus 1 over x squared. So it's going to be plus 1 over 2 sigma to the 4th. It's going to be n here. And then this sum, which doesn't change at all. Okay, and this should be 0. So if you do the algebra, you get the estimator for sigma squared to be what? Sigma square estimate ml. We give you, because of this and this here, I can multiply everything by sigma square. What I get, 1 over n, the expected. Here I actually assume that I already know the estimator, the best estimate of mu. So it's going to be sum over n. To be a little careful here. It's the empirical variance. So it's actually the estimate. Okay. If you don't believe me, check this. I say check this as I usually want you to do this small exercise.
You were missing a minus before the first term,
before the first term, yeah, absolutely. Otherwise, it doesn't work again. Okay. Notice again And we'll see this after the break. This is some sort of a biased estimator, which means something which I'll explain later today. And in other cases where you have a prior, you may have other functions here which depends on the prior, just like in the estimate. So, but it's very intuitive. So the estimate is simply the variance mean. When you first estimate the mean, and then it's the sample mean. Yeah, that's what I mean by that. It's the sample variance. Again, or the empirical variance. You first estimate if you have a cloud of points, even in 2 dimensions, and you assume it's coming from a Gaussian distribution, the mean will give you the empirical mean of this. This is the best estimate, and then the best estimate of your variance is the variance of the sample, the empirical variance with respect to this estimated. Okay? I cheated just a little bit here when I replaced mu by mu estimate, but think about it. Should I do it? Is it okay? It's okay. Okay, we'll take a break. I don't.
No, for here, if you derive with respect to the mu, doesn't these two cancel this two?
It doesn't matter.
Right, I know. But I'm going to be proving it later. I want to make sure it's not two.
Cancel this. This is why you put this together. This is why Gauss wrote it that way. זה נשאר מיוט. זה נשאר, כן, זה נכון לכל מיוט שהמינימום... אבל אני החלפתי את זה בזה, כי זה באמת unbiased. אם היה לך... אני צריך לחזור על זה. אם היה לך תלות הדדית? בצורה ביותר תלות הדדית? במיוט סיגמה? לא, זה עדיין לא משנה. אני לא הנחתי כאן אפילו של מיוט סיגמה באיזשהו מובן משתנים מקריים. אבל יש מיוט סיגמה. אני אחזור על זה עוד מעט. זה דבר ששווה יותר שהוא מסביר משמעות. אבל זה לא, זה מה זה תלות? זה מניח של תלויים ספציפיים? בסדר, אז יכול להיות שפה יש לי גם... אם למשל אני יודע שסיגמה הוא מיו בריבוע, אז כמובן שזה לא פרמטר דיפרנציאלי. לא, ברור. אז לא, אז יש תלות פונקציונלי בין הפרמטרים, בעצם זה אומר שהמרחב הפרמטרי יותר קטן מה שחושב. אני מבין לך, אבל... זאת אומרת, אני מתייחס אליהם פה כבלתי תלויים, ואני יכול לגזור כל אחד בנפרד. אם אתה אומר, לא, מיו בעצם איזושהי פונקציה דטרמיניסטית של סיגמה או סיגמה, אז כמובן חשוב לעשות את זה. לא, אני אומר סתם, שאתה מחפש את המינימום, פה היית מקבל משהו בסיגמה. אם המיו תלוי בסיגמה? לא, באופן תיאורטי, באופן מקרי או לא מקרי, זה לא תלוי בסיגמה. חשוב, אבל זה לא חייב לקרות. אם זה לא... לא, במשפחות כלליות יותר, זה בטח יכול לקרות. ואז אתה לפתור את המשוואות האלה ביחד. כלומר, יש לך דמרים שמשוואות כל הנגזרות של הטקסט. אתה יכול לפתור מערכת משוואות, יכולה להיות לא לינארית ושליפה. במקרה של גאוס זה לינארי יפה, אבל צודק, באופן כללי, המקסימום רק כדי שאני יכול לתת לך משוואות לא פשוטות. במקרה הכללי זה... לא, במקרה הכללי, אנחנו נדבר תכף על איזשהו פעולות של זה, משפחות אקספוננציאליות אבל כללי. מה שנקרא אקספוננציאל פורמס. לא יודע אם תזכרתם. במקרה הכללי באמת, החיים נעשים יכולים להיות מאוד קשים, ומקסימום רק זה יכול להיות לא קיים, לא יחיד, לא קל למצוא אותו, כל מיני דברים לא ידעים.
זה אף אחד לא אמר לך שהוא קיים ושהוא יחיד.
נכון, לא אמרתי. זה הקיום והיחידות שלו, זה תראו בתרגומים.
קטע מגיע
תראו דוגמאות שבהם הוא לא קיים, זה לא יחיד.
אבל אז זה אומר שטלטה מגיע מאיזשהו טווח שהוא לא קומפקטי.
נכון, אז יש כל מיני צרות. טלטה נמצא בקטע טלטה, למשל, כבר כזה שצריך כל מיני לעבוד על זה. גוצ'י, נותן כל מפגן דוגמאות מהסוג הזה, תראו דוגמה כזאת.
כאילו, אם היית צריך כבר בתור...
באמת שמה אתה מקבל שהאקטיבית הוא לא פונקציה כל הזמן, פונקציה של אחד יותר גדול. וכל מיני צרות ואז הסטפה יוצא המקסימלית לא קיים, כל מיני אנחנו לא אוהבים אותם, אנחנו מנסים לעבוד עם
אבל אתה מוכר אותך לעשות את זה דבר
מגיע לים זה איזה משפחות זה בעצם חזות לנו, זה מה שנקרא exponential family.
איך המוח שלנו זה לפי איזה, מה הפונקציות המחיר?
המקסימום על המוח.
לא פונקציות המחיר שהוא לוקח.
שאלה מצוינת. בדרך כלל אנחנו בוחרים משהו נוח, אבל אני אדבר על זה בשבטות, כרגע לא מדבר על המוח.
אתה לא יודע איך קופים עובדים, יש מאמר באינטרנט. סתם, טוב, אתה לא באמת יודע, אבל...
לא, אנחנו משתמשים מה שאנחנו יודעים, מתמטיקה עוברת לנו עד נקודה מסוימת. אנחנו חושבים מה שנוח לנו לעשות את זה.
אבל בוא נגיד, ברגע
למרות שהתפקעת את זה בצורות, רגע, המקסימות האלה לא קיימים.
זה הבעיה של
אז נניח, זה מה שקוראים כאן technical assumptions. נניח שההסתגלות שלנו היא קומפקטית, אנחנו נקבל בתוך סכום כך שאפשר לפתור את זה על ידי תשובות. יש מקרים כאלה אחרים, יש כל מיני פתולוגיות מתמטיות. אפילו מתמטיקאים אוהבים לדבר. בטח אנחנו לא אוהבים לדבר.
ורציתי עוד שאלה אחת לגבי השיעור הקודם, שהוכחת את זה, ואמרת שזה רק נותן לי אלפא ועוד בטא, קטן או שווה מאלפא אפס ועוד הבטא אפס של הכלי. וזה לא נכון עבור אלפא ובטא באופן.
לא נכון שאלפא קטן מאלפא פריים ובטא.
לא הבנתי למה לא.
כי לא שהצלחנו לקבל, הצלחנו להראות את זה.
לא, אבל...
גם קיבלנו את הרשמה הזאת. קיבלנו שאחד מינוס אלפא פריים חלקי בטא פריים גדול מאחד מינוס אלפא חלקי בטא. וקיבלנו עוד משוואה שהייתה אלפא פריים חלקי אחד מינוס בטא פריים קטן מאלפא חלקי אחד מינוס. נכון? קיבלנו שתי משוואות, לכאן הגעתי. עכשיו מתוך זה תנסה לי, מה שאתה יכול להוכיח זה רק את זה לצערי. שאלפא פריים פלוס בטא פריים קטן שווה מאלפא. וכמו שאמרתי, זה לא נורא, זה ביקשתי מכאן לעבוד על זה. אמרתי את זה כתרגיל, אמרתי שאתה רואה. זה מאוד פשוט. כופל באלכסון, מסתדר את הרנדורים. רציתי שתראו שזה מה שנובע מזה. עכשיו, אני לא יכול להגיד יותר מזה, אבל זה מספיק. זה מספיק שזה אומר, כמו שאמרתי, שה-R סופר, המבחן החדש, הוא לא יותר גרוע מה-R סופר. אני לא צריך שאלפא פריים קטן אלפא בטא. זה בדיוק מה שאני אומר פירסון אומר. באותו אלפא, הבטא יותר קטן, אבל באותו בטא, אלפא יותר קטן.
הסתכלתי על ההוכחה הזאת שוב, ואני חושב שלא הבנתי למה אני לא יכול לעשות אותה טיפונת שונה, ואז לקבל שאלפא קטן.
אם תצליח לעשות את זה, אני מאוד יודע לך הרבה אנשים יודעים לך. לצערי, זה כתוב בספר, אבל זה לא נכון. אני בפעם שאני שמעתי את זה, זה מסוגל להשתמש בהוכחה. אמרתי את זה, אבל זה לא נכון. זה מה שלא.
אז אני רוצה להבין איפה אני טועה.
אני לא הוכחה, אבל אני הרבה אנושות עכשיו, סלח לי את זה. אני לא מאמין אני יודעת את זה הרבה מאוד פעמים. אין הוכחה, אבל אני אומר, זה מה שאנחנו יודעים להוכיח, וזה מה שאנחנו צריכים. אנחנו לא צריכים.
כאילו, אתה מתחיל מאלפא 0 לבטא 0, שזה המטרה שלך.
אני מתחיל באיזשהו אלפא ובטא. עכשיו, אני קיבלתי, אמרתי, יש לי איזשהו A של אלפא ובטא.
זה ה-A וה-B. זה ה-A ו-B.
נכון, זה ה-A ו-B. עכשיו לא, עכשיו אני הראיתי שזה גדול מ-A. וזה קטן מ-B.
אני אומר, תגדיר פשוט את A.
זה מה שהראיתי, ראיתי את זה ואת זה, שני השלישונים האלה.
לא, תגדיר את A להיות זה וזה. הרי אין לך A ו-B.
לא, אני אומר, ראיתי שעבור ה-A ו-B שנותנים אלפא ובטא, עבור ה-A ו-B שנותנים אלפא ובטא, אחד נמצא בחלקי בטא גדול שווה ל-A,
אז אני אומר,
של אלפא ובטא.
תעשה משהו אחר.
זה לא עושה.
אני אומר, תעשה משהו אחר.
זה מה שהראיתי. עכשיו, מתוך זה, אמרתי, אוקיי, בוא נקרא לזה עכשיו A פסיק. ונראה מה אלפא ובטא שלהם, וזה גם אלפא פסיק ובטא. קיבלתי אותו שני השוויונים האלה.
אני אומר, תעשה משהו אחר. יש לך אלפא ובטא שהם היעד שלך, נכון? זה מה שיש לך. תגדיר את A להיות 1 מינוס אלפא חלקי בטא, ואת B להיות אלפא חלקי 1 מינוס בטא. ואז כשאתה מחשב את האלפא,
אמרתי, קראתי את A פריים. זה A פריים שווה לזה. השגיאות שלהם, הפריימים, זה כל מה שאני יכול לראות, שזה גדול מ-A פריים וזה גדול קטן מ-B פריים. זה צריך אותה הוכחה. לגבי הפריימים. אם יש לך הוכחה,
בשעה מאוד ספציפית בהתקרבות כנראה. למה אני זוכר בזאת? סתם הייתי חדש חודשים. למה אני זוכר בזאת?
לא, זה לא נכון. זה הקריטריון המקסימלי. אני חוזר את הלייקיות לפי הפרמטר. אני משתנה.
אוקיי, אבל פה כבר רצית את זה.
עשיתי את זה עבור מיוט. יש הפרמטר חדש. פרמטר יותר.
אוקיי.
עשיתי שניהם שאני צריך לספק.
אוקיי, תודה. חשוב מאוד. שאלה קטנה, משהו באמת קטן לימודים, במקסימום לייט לימוד אתה כותב משהו כזה, ממש בקטן, לא להפריע, פי של x, והוא מופיע בתוך איזשהו ביטוי גדול יותר, כתלות באומגה 0. פשוט זה היה לא בלייטיות.
עכשיו כבר אין אומגה 0, יש לנו תטא.
מה המשמעות של הדבר הזה?
זה אומר שהעולם נמצא במצב אומגה 0, במצב הזה זאת ההתפלגות שלו.
זאת ההתפלגות שלו. בכל זאת, אם לא היה אומגה 0, אם היה לו רק x, היית פשוט כותב x. ואתה אומר, x בהינתן אומגה 0, כל המשתנה המקרי הזה.
אני מדבר על ההגדרה, זאת המדלת של x באומגה 0.
אוקיי, זה בעצם היה סימון
זה סימון חשוב מאוד.
אוקיי, בסדר. תודה.
כן, זה פשוט הגדרה של התפלגות מובנית, כי אני יכול להיות ממש. אוקיי.
רגע,
כן, לא, עד פה, זה הגיוני. ככה אתה הכי סביר בהינתן
בעבודת הורים מסתכלים על דאטה
אבל
כל מיני רמות של
גל, אוקיי.
שאלות הנשאר
אני פשוט הבלעתי אותך במעבר מהאסטימטור למקסימום.
אז אני עשיתי דבר מאוד פשוט, כתבתי את זה כמכפלה של הפריירות בלייטים.
לא, רגע, אבל אמרנו את זה.
זה המקסימום.
אוקיי, שזה כמו
זה לקחת את המקסימום של המכפלה הזו.
זה אחר כך.
לא, זה לא אחר כך, זה עדיין זה. המקסימום של זה המקסימום של זה. נכון? כשפת ב', כן, סוף חלקי אין, אבל זה לא משנה.
את המעברים אנחנו
עכשיו אמרתי, זה שווה למקסימום של הסכום הזה של הלוג פריור, פלוס הלוג לייטיות. נכון? עכשיו אמרתי, אבל הלוג לייטיות שאין גדול הוא הרבה יותר גדול מזה. אז הפונקציה הזאת שולטת על זה. אני קצת לא מול, אתה מרגיש שלהם. כי זה לא אומר שהמקסימום לא משתנה. אבל בעיקרון זה פונקציה קטנה.
למה הפרייר הוא קטן
זה O של 1 וזה O של N. כשאין גדול, זה שאלתי אחר כך, זה המקסימום של הלוג, עכשיו זה מספר שהוא O של 1 במובן הזה שהוא לא משתנה עם N. נכון? זה רק בפרייר. וזה הולך לגדול עם N באופן לינארי. אז הפונקציה הזאת, קומבינציה נעזרה ומחלק ב-N. זה הולך מפת כ-N, ולכן זה ב-N גדול ילך ל-N. הוא לא ישפיע עליו. זה בדיוק כל שאמרתי.
אבל אני עדיין מחפש מה השורה התחתונה של כאילו, מה האסטימטור הזה. אם אני מחפש את המאפ אסטימטור,
אז אתה יכול לקחת את המקסימום של שתי הפונקציות של הלוג לייטיות של הלוג פרייר. המקסימום שלהם יכול להיות בפונקציה שנייה.
לא אמרנו שזה השכיח
זה השכיח של הפוסטריות. זה השכיח של הפוסטריות. והפוסטריות מושפע מהפרייר.
אוקיי. אבל נניח שיש לי את הפוסטריות.
יש לך את הפוסטריות, זה המקסימום של הפוסטריות. אבל הפוסטריות, זה באמת חשוב להגיד את זה. הפוסטריות הוא דבר אחר נכון לעשות.
1, זה אמור להיות 10. עכשיו, נניח שראית עכשיו סאמפל שהוא פה. אז הפוסטיריור יהיה מוטה עכשיו. פוסטיריור... אז הפוסטיריור יראה עכשיו משהו כזה. יזוז הנה. הוא יהיה מושפע קצת מזה וקצת מזה. כלומר, שהפרייר, המדגם הוא גדול. מה שאני אומר שהמדגם הוא גדול, הוא כמעט יתעלם מהפרייר. אז הפוסטיריור יהיה פה. מקסימום פוסטיריור יזוז הנה. זה בסדר. אבל ככל שהמדגם יותר גדול, ההשפעה של הפרייר תהיה יותר קטנה, זה לא חד מקיים. לכן, אסימפטוטית, המקסימום הפוסטיריור הולך למקסימום לקטן. כלומר, זה אנחנו יכולים להוכיח, תקע מקסימום הולך לתקע ML שאין הולך אם הפריור הוא well behaved, זה לא היה סוף. לכן, בואו נסתבר עם פריור, גם סוף המתמטיקה וגם סוף הקונספטואלית, נניח משהו על פריור פרמטר, בואו נעשה סתם משהו. טוב, רבותיי.
Okay, so I had, as usual, the questions during the break are very important because they really let me know what you go to, where are you with respect to where I assume you are. So this feedback is really critical. And so there are some very good questions here. First of all, so probably you didn't do it enough examples. You have to do more of actually calculating both the maximum a posteriori estimate and the maximum likelihood, so we'll make sure that you do some. Without this, you really don't feel the thing, but what is really important is that the maximum a posteriori, especially if I divide it by n, so this shouldn't change if I divide it by n, and as I said, this then will be O of 1 over n, and this will be O of 1, and eventually the effect of the prior is going to be negligible for n goes to infinity, which means indeed that the maximum a posteriori and the maximum likelihood are going to be asymptotically the same. Okay, so this is, I would like to do maximum a posteriori. This is what the Bayesian theory is telling me. It's problematic both because I have to invent a prior, or to justify a prior, and because mathematics is somewhat more difficult because I have to take derivative of two functions and then solve this equation equal to 0. And in general, it's going to shift my, unless I am choosing a very nice prior, like conjugate prior or things like this, which will make things simpler in terms of the mathematics, but in general, it can be a lot more complicated because the prior can be complicated. So this is why we choose nice priors. But maximum likelihood is telling me, look, you don't have to care about the prior as long as it's proper. I mean, it's not 0 anywhere. It's going to be asymptotically ineffective. It's not going to do much. Of course, the posterior is always shifting a prior to the data in a way that depends on the data. So in this case, if the prior was Gaussian, which is conjugate to Gaussian, and the data is also Gaussian, the posterior is also going to be Gaussian, but it's going to be some sort of combination of the two Gaussian. It's going to shift the distribution a little bit. This is the first thing. The second thing is that, of course, when I take derivatives with respect to two parameters like this, I actually assume some sort of functional independence. So for example, if I assume that mu and sigma are two different parameters, if for some reason you have connections between them, for example, you know that mu is sigma square, or sigma is mu square, or something like this. Sigma square is mu square, by the way, for some distribution, for example, the Poisson distribution. So it happens. So there are cases where there are connections between parameters, which means that I cannot take derivatives just like this and assume that they are independent. But what it means actually that your dimension of the parameter space is smaller. They're functionally connected. If they're only statistically connected, which means that some don't, then usually I don't worry about it. But of course, the equations, the maximum likelihood equations, taking all the derivatives equal to 0, is a set of coupled equations in general. That's exactly where I cheated you last for the break. So I actually have to solve these two equations together. This one and this one. It's only here in this special case, in many other special cases like this, that if you take the derivative with respect to one parameter, you actually get an equation for this parameter irrespective of the other one. You get total independence. But here, for the sigma, I actually got mu there. And by replacing it by mu hat, as I said, I cheated you. What I had to do is to show you that mu hat and sigma hat are the solution of these coupled equations. And these coupled equations are in general can be very complicated. And they may have no solution at all, or multiple solutions, and there are many mathematical difficulties that can be there. Usually we assume that that we have a nice parameter space, which I'll define in a second, which is called identifiable models, where this is well-defined and well-defined problem. And mathematically, these two equations are actually coupled. I have to solve them together. Okay? And in general, there are nonlinear coupled equations, which can be a nightmare to solve. So we are actually going to look for interesting families where things are simple, and parameters which are what we would like to call natural or easy to treat. For example, here it's mu and sigma square, but in general it's not necessarily the parameters of the distribution. It can be some transformation of them. And those of you who see where this can take you, I mean, it can take you to very interesting mathematics of actually the geometry of the parameter space, which I'm not going to talk about here, but it's actually very interesting. It's called information geometry. Okay, so I want to continue with properties of maximum likelihood estimators. So what do we really want to show? So since it's not a Bayesian estimator, we know that it's going to be close asymptotically or identical asymptotically to the maximum a posteriori. But again, there are some other properties. And actually, I mean, the literature is, since it's divided between statisticians that are Bayesians and non-Bayesians, you can see books that are completely ignore priors and talk only about maximum likelihood and name and Pearson without prior and so on, and avoid priors, especially about parameters. And you can see other books which are more Bayesians that have usually assume priors on the priors and parameters of those priors, which they call hyperparameters, and so on and so forth. I mean, it can go forever. And it's really a nightmare, but this is what the Bayesians do. So in our case, we want to, it's not important enough for me. What in practice, maximum likelihood is a very sensible estimate in many cases, and we want to show why. So the first thing to show is something called consistency. Which is, so we want to make sure that the parameter in the limit of n goes to infinity actually goes to the true parameter. So this is essentially the requirement that the estimator is approaching the true parameter in the limit. But then, for those of you who are more mathematically sensitive, I have to specify exactly what I mean by this limit, because this is a random variable. Okay. So this random variable is, which means that I have to say something in probability. And what I mean by this is essentially that the probability that theta hat xn. So why is it a random variable, by the way? Because it's a function of a random sample. Okay. So the sample can be very bad or very good, or complete. I can have a, for some reason, completely off sample, which will shift the whole estimation to the wrong place. So in some sense, we need to think about this. This is a random variable because it's a function of random variable. So we want to say that this is going to approach n, to approach the true parameter in probability, this is what we mean. That the probability that this doesn't happen is small. Or actually, I want to say we can say something much more careful. I mean, the probability that the difference between this is larger than some epsilon. There exists n large enough such that this is greater than 1 minus delta for any delta, or things like this. But this is what they mean by limiting probability. So essentially, almost all samples, when they are large enough, will be good, in the sense that they are going to converge this estimator to the true parameter. Okay, so consistency. So actually, it's interesting to prove it, and of course, what we mean by that is that we say that an estimator is consistent if it's in the limit going to approach the true model. So of course, for that we need to assume that the model is actually well defined. I mean, in the sense that there's only one set of parameters that give you a certain distribution. So we assume that the model is identifiable, that the family, the parametric family, px given theta is what we call is identifiable. So this is what called identifiable in the limiter. And this is an important property, which means that what we mean by this, that if the DKL between two distributions of this family is 0, then this can happen only if the parameters are the same. And this is essentially the definition of identifiability. So, which means that if the two distributions are essentially the same as distributions, the parameters are also the same. So we cannot have two sets of parameters for the same distribution. Okay, so this is just a simple assumption. Usually this is the case. For example, think about Gaussians. If either mu or sigma is different, we have a different distribution. But if I have some sort of dependency between the parameters, or have redundant parameters, then it may not be true. There may be different sets that have the same. So this, assuming identifiability, we can actually prove that the maximum likelihood is consistent. So again, we are using this DKL all the time. So essentially what we want to show is that the limit, so theorem if you want, that theta ML is consistent if for identifiable family. Okay, so what should I be consistent in the sense that, so I have to take the limit of n goes to infinity of the maximum. Yeah, let me write it more carefully. I have to take of the argmax, the limit of theta maximum likelihood is what? Is the limit of the argmax the argmax over theta of the log of 1, I'll write it like this, 1 over n log px n respect to theta. Okay, this is just my definition, okay, of theta ml. Theta ml was the argmax over theta of the likelihood, of the 1 over n log likelihood. Okay, Now here you have to be a little careful, then, because now I'm actually, here I said, okay, multiplying by 1 over n doesn't matter, because it's a constant, but now I'm actually taking n to infinity, so I have to be very careful with limits like this. I mean, but if I'm not careful, or if I'm doing what the physicists do, so you have to, I can exchange the limits with the maximum. Okay, and this, if all of you jump on me here, you're absolutely right. But if I can exchange the limit, so this should, I put a big question mark here. Here you have to be careful. You have to know what you're doing. So in principle, I can take, it should be maybe equal to the argmax over theta of the limit n goes to infinity of the log likelihood. So this is a very tricky exchange. I mean, whenever you exchange limits like this, you have to be careful, as mathematicians can tell you. It's not always true, but we assume it. Okay, we assume it to be true at this point, and of course it's a property of the family, and in general it's not obvious at all. Okay, but then I can use what I already know, which is so if I assume here IID, this 1 over n log likelihood in the limit, if I assume IID, so this is a sum, this is a log sum. Okay, let's write it another line. Limit n goes to infinity of 1 over n sum log pxi over theta. So here it's actually convenient to assume IID. So this is, again, the sum over a sample. But we already played this trick before. So a sum over a big sample is going to look like the argmax over theta. So this precise limit, when I divide it by n, is going to look like the argmax over theta of the sum over x. The sum or integral, depending on, when I write sum can be integral in the continuous case. The sum over x of what? Of p, the true one. Now here I have to be a little careful. That's why let's denote this by theta prime. It doesn't matter here. So far it was theta prime here. But here I actually have to be careful, because my sample came from the true theta, the true parameter of the world, if I assume it to be true. So this came from the true theta. So n times this is precisely the number of times that this particular x will appear in the sample asymptotically. Okay? So this is exactly the same trick that I used already before. Times log p of x given theta prime. Okay, it's important, and this is prime. It's really important to make this distinction. So theta prime is the dummy argument with respect to which I maximize, and theta, this is the true theta, where the sample came from. Notice here that I assume what we later will call proper learning or proper estimation, that my sample actually came from this family, that there exists a true theta. If this theta doesn't exist, then we do something slightly different. Not very much different, but like this. Okay, so, but then what this is very close to, so it's sigma p log q. Okay? If you remember, so this is some sort of sigma or expectation of px log qx. This is something of that form. Okay? Where p is the distribution of the true data, and q was my model. So it's an average respect to one distribution of a log of another distribution. Okay? And you see why it's not the same distribution? Here I didn't take So this I can write as what? I can write it as minus the DKL between Q and P and Q, plus, and what did I add here? So plus the sum over X of Q log Q. I'm sorry, of P log P. And again, I'm very cruel to those people at the end. So this is again something we actually used. Let me write it again more carefully. Okay. So this was a little aside. In general, some P log Q is minus the DKL by minus because I need Q to be in the denominator. But then, so it just write the definition of a DKL. Okay. This is, by the way, something we will later on call entropy, or minus entropy actually, of the distribution. So essentially, just write it again, because if you want to prove it very quickly, this was the sum over X of Px log Px over Qx. Just a reminding. So I've just opened this, and you see exactly why this is true. Okay. So notice, so I can write this. I write it here. So this is simply the argmax of a theta prime of what? So I want to apply this little lemma to this. So what is it? Of the DKL between the true distribution and the model distribution, the unknown. So this is, by the way, X here is now the single sample distribution. I already used the N here and average. So this is it, plus something which is independent of theta prime. Okay? So this depends only on my true theta. So it's entropy. Okay?
Shouldn't it be arg mean because it's minus?
Yeah, it should be minus. Sorry. Okay? So I simply use this, wrote it like this, and notice that this, the entropy, or this particular sum of the true distribution is independent of theta prime. Okay? If it's independent of theta prime, when I take maximum or maximum in, it's not going to affect it. Okay, so this is just this. And okay, so this is nice because this is going in the limit. So essentially, maximum likelihood is equivalent to comparing the empirical distribution to the, here, I already took the limit and goes to infinity, but I could use this earlier without the limit and say that this is simply the empirical distribution, and this is my model distribution. So essentially, or if you want, just to make it easy for some of you, this is the arg mean of a theta prime of the d px theta to the empirical, this is the empirical distribution given the true theta. This is, in general, it's the empirical distribution. If you don't see this, think about it for a second. And this is my model class. Okay, but now, because we said that how does it prove consistency? So I need another line. Something is missing here in my notes, but so why is it showing consistency? So again, using the identifiability, the minimum. So the minimum here what is the minimum DKL? 0. When will it be 0? When theta prime is with theta. So this will be 0 only when theta prime is equal to theta. That is, here I'm using the identifiability, so this is theta.
Which one of the distribution is the empirical one? The theta prime or the theta?
No, the theta prime is the one I'm minimizing over, and theta is the true one. So this minimum DKL will be 0. The minimum will appear only when theta equals theta, and this is here I'm using the fact that it's an identifiable family. Okay, it looks like magic, but it's very simple. Okay, so by the way, if it's not in the family, you already see what happens. Then this minimum will not be 0, because there's no distribution in my family that precisely matches the asymptotic distribution of the sample. But then it will be the closest in that sense. It will be what we later call a projection, in some very special type of projection. Otherwise, it's simply the one which minimizes the KL distance to the family, or the KL divergence. I don't want to call it distance, because it's not distance. So you see that essentially what you do here is you project the data on the family and look at the point which is closest in the DKL sense to the distribution. So it's some sort of a projection. It's called eye projection in some circles. Eye projections of the empirical distribution to the family. So it's very much, if I draw a little geometric picture, if this is my parametric family, think about each one of them is actually a distribution. And my data is somewhere here. It will throw it to the point theta ml, which is the closest in this DKL sense to my data among all the possible distributions. So this is the family theta. I can think about it some sort of a manifold of parameters, and this is the projection to this manifold. If this was beyond the head of some of you, forget it. It's not important. Okay, so maximum likelihood is actually looking for the closest possible distribution in the DKL sense, in this particular DKL sense, between the empirical distribution and my family, parametric family. So we also showed that if my data actually came from this family, then it will give me the consistent estimate. Okay, so this was a little tricky, but it's good to know. Questions about it? So the next and very important topic, I'm already behind my own schedule, but it's all right. It says, okay, so we have consistency. What is the next important thing to say? So the next important thing to say is actually related to two quantities. When I have an estimator, it's a random variable. One thing I want, so it's a random variable, it means it has some distribution. As you're going to see in a maximum likelihood, the distribution of the estimator in the IID case, due to the central limit theorem, is actually going to be Gaussian in most well-behaved cases, because it's a sum of IID random variables which have variance. So it actually has a mean and what. So it's really characterized by two numbers. If it's going to approach asymptotically a Gaussian variable, so theta hat itself, this is a little hand waving, but it's true. So theta hat asymptotically for IID samples is going to behave like a normal distribution with something which we may call the expected theta hat, and something which we may call the variance of theta hat. This is in general true. Generally true, though I didn't prove it yet. But this is a simple consequence of the central limit theorem. If this is not clear, so this is essentially the central limit theorem. Applied to this sum of to theta hat, but it needs to be argued more carefully. But if this is true, then there are two things which I really want to care about. What are they? The mean of the this is, by the way, the mean over all samples. Yeah? over samples, and this is the variance over samples. So I want to argue, so the mean should be what? What I would like to have. Just like consistency, I want the mean to be on the true parameter. This would be nice, okay? Consistency only shows that asymptotically I approach the right parameter. But so this is a different property which we want to call unbiasedness. Or there's another thing which we want to call the bias of the estimator. So the bias of the estimator is how far the mean is from the true parameter. And the other thing which is as important or even more important is the variance of the estimator. So actually, this is really it's getting really deep in the sense that it's something which is a fundamental property of estimators, which is going to take us a long way into the course as a general property of learning the bias and the variance of an estimator. It's so fundamental that sometimes it's called in some books the bias-variance dilemma in some sense of learning. So I can't really exaggerate here. So the question is, okay, so we define something we call the bias of an estimator. The estimator theta hat. So remember again, it's a random variable. So it has an expectation, hopefully. So the bias of theta hat given theta, this is just definition, is what? The difference between the expectation with respect to the sample of theta hat, just to make sure that it's really a random variable function of the sample, minus the true theta. So how much is this expectation shifted with respect to the true theta? If I estimate it and the mean is not where it should be, then I say that it's a biased estimator. Okay? And the variance of the estimator, what should it be? So the variance of an estimator, what is it? How is it defined? Okay, it's the expectation of theta minus its expectation square. Okay? So the variance of the estimator theta is, again, the expectation with respect to all samples, conditioned on theta. I should really emphasize it. It's conditioned on theta. And of this theta hat minus theta minus the expectation of theta hat. The expectation, so again, conditioned on theta. So it's a conditional expectation. Sometimes we write it expectation condition on theta. It's square. Okay, so this is the variance. Okay, just the definition of a variance. Okay, so how are these two things related to each other? The bias and the bias and the variance. This is really an important statement. So in general, we are talking about what we call the least square error, or MSE, mean square error, which is what is the expected. The only difference between what I called L square before is that there we actually took the average with respect to the posterior, and here we take the average with respect to the likelihood itself. So what I really want to see is what is this? What is the expectation over all samples condition on theta? I just ignore the notation of probability. Of course, it's the joint of the likelihood function. So the likelihood function, condition on theta of theta hat minus theta square. This is the mean square error. This is what we really care about. Okay, so this is just like the least square error, but I average here with respect to the likelihood function of the respect to the posterior. That's the only difference. So this is really the mean square error, if you want. How much this is different from this. Okay? So this is the true parameter. true, and you can see that the true assume that I'm properly sampling from the same family. If it's not the true one, it's actually the closest in the DKL sense that I just mentioned, but let's assume that this is the true parameter. So what is it? What is it here? So when I actually assume true, I mean that the sample was taken from this distribution. That's what I mean. So this is called the mean square error. Now, what is it? Now I can play a usual trick that you may have seen. So I don't have too much time, so I'll do it quickly. So this is, I can add and subtract the expected. So this is the same as theta hat xn minus the expected theta s plus the expected theta. Notation is terrible. So this is nothing minus theta. Okay, square. I can always do that. Okay, so I added the mean of the estimator and subtracted. Okay, but now I can use the important formula that a plus b squared is what? What should I write? Okay, I know that this is something you may want to see. So I use the fact that I actually wanted to get all the way to Kramer-Rao bound today, but I see that it is not going to happen. So so this is just the sum. So this is equal. I can take this as A and this as B. Write the A and B, and use the fact that A plus B squared is 1. So this is the expectation of the first term square plus the expectation of the second term plus 2 times the expectation of the product. Okay? Should I explain it? No. Sometimes I'm not exactly sure. So this is going to be the expectation of theta square, theta xn minus the expectation of theta square plus the other one, the expectation of this, the expectation of theta hat minus theta square. So this is the a square plus the b square, and there's a 2ab, and the 2ab is 0. Okay, you prove it. Why is it 0? Sorry, plus 2 times the expectation of the expectation of theta hat minus the expectation of theta. That is enough for me. Plus, and this is the first term, so it's this one times this one. So here it's this minus this, and the other one is this one, the expectation of theta. Yeah, it's too many expectations. Expectation of theta xn minus theta. So this is the 2ab. This is the a square, this is the b square, and this is the a and b again. But notice that this is 0. Why is it 0? This term. So the expectation. Okay, so this is 0 because this expectation of this is this. Okay. And here, okay, I have to be a little careful when I do this. Expectation of a product, what is it in general? So expectation of a product is not the product of the expectations, unless what? Unless they're independent. But in this case, I can do it. Just think about it, why I can do it. So it's really the product of this expectation by this expectation by this expectation is 0. Because the expectation of theta 8 is precisely the expectation of theta. And the expectation of a sum is the sum of the expectation. So first of all, I'm using two things here, that these two things are independent. And because this is already expectation, so this is just a number. So there's nothing here. So this is 0. Show. Convince yourself. The whole thing is 0, so what I'm left with the variance of theta hat, given theta, plus the bias square. Okay, this is nice. Okay, so the mean square error, which is really what I care about, I mean, how close I am to the true parameter, is the sum of two terms. One is precisely the variance, and the other one is precisely the bias square. So now here is the dilemma. You want to minimize this. This sounds like a good idea, but usually I can't minimize both of them together, and there's some sort of trade-off. If I make, for example, theta very rich, allow a lot of thetas, I mean, everything I'm saying now is not true if my theta is an unbiased estimator. If I have an unbiased estimator, and we'll come back to this in a second. But if it's biased, which means that maybe you are not really learning with the right family. I mean, maybe the sample comes from 1, and actually, so then having a richer family is going to decrease the bias because I have more thetas to fit. So I can probably get closer to the richer, but it's going to increase the variance in general. So if I have a rich family, a lot of parameters that I can fit anything, I can, in general, reduce the bias, but I pay with the variance. So this is a dilemma. We're going to come back to it later on in learning, and we'll talk about learning in general. This is essentially a trade-off between overfitting and generalization. I mean, if I want to reduce my bias to 0, unless I know that I come from the right family and I can do it, and actually have an unbiased estimator, this has a cost in variance, which means that in many cases, I actually don't want to have an unbiased estimator. But if I can, if I can make this 0, then we are then the whole mean square error is just the variance of the estimator. So again, this may be a little too abstract at this point. What do I really mean by this trade-off? I mean, but in general, think about it. I mean, you want to fit the distribution to data. You are not sure that the data actually came from this family. So I want to fit a Gaussian to data. Maybe, who knows, it's a real-world data. What should I do? So the question is whether I want to choose a richer family which will allow me to really nicely fit the data. But then I may pay with the variance, which is too large, and then my mean square error will be larger than I want. But maybe a little bias, which means smaller family, will actually reduce the variance enough to have a much better mean square error. So this is really the basic dilemma of statistics, and also the basic dilemma of learning. And we're going to solve it again eventually by talking about something else, which is the generalization error, which is a much more fundamental thing. But at this point, and this is the end of my class today, we say that we want to talk about unbiased estimate.